This meeting is being recorded.
Okay. Yeah, so we started the recording because we want to start with computations. And today I will be focusing on using the integrals as a way of transforming things and in particular computing numbers. And the first motivation I want to show you is something called an integral operator. So I could consider a function g, which is a product of applying some integral operator k to a function f. And its definition is that at any point z, it would be defined as an integral over the real numbers, dz prime. And then I have the kernel matrix. So this is like basically matrix multiplication. And then here I have fz prime. Okay. So this could be the Green's function for Gaussian systems and so on, anything you want. And today we will look at different ways of trying to view Grassmann integrals as basically integrals and not derivatives. So for example, one thing that I want to show you is that let's consider different examples. So the first example would be to consider something that I will call delta. And the delta will depend on G and P and will be defined as an ordered product G1 minus P1 dot 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 until G2L minus P2L. And those G's and P's are the generators of a joint Grassmann algebra. So we will have a Grassmann algebra generated by G1 until G2L. This is not touching correctly. This is G2L, and then P1 until P.
Yeah, I remembered that the pen had run out of battery, so I hope.
I got new batteries,
Okay,
but it's somehow
awesome.
well, yeah.
Thanks.
So I can use the fingers sometimes. Okay, so I will repeat what is written here. Sorry about the pen. Basically, we have a Grassmann algebra generated by symbols that I write with two different characters, but they are all anti-commuting with each other. And the point is that this will be behaving as a delta, Kronecker delta or Dirac delta. So for example, K could be a Dirac delta as well. So for example, Z minus Z prime. And that would be the equivalent for function spaces. So let's do a computation. So I will integrate against P, and I will integrate against G. Is that how I want it? No, I want to have only one integral. So I will integrate against G. And basically all Grassmann functions are basically Grassmann polynomials. So it makes sense to consider what happens if I take this Grassmann variate function that I just defined for some g of mu, where g of mu is what we had always before. That mu is telling me whether I take a Grassmann number or whether I'm not taking it. So it goes until G to L, and then mu to L. This is at 2, and mu is from 0, 1, and it's a binary string here. Okay, so what's going on here is that that basically what happens is, maybe I will make a simpler computation. Let me integrate over against G1. Maybe when I'm touching. So just G1, and then I have G1 minus P1, and then G1 mu 1. Okay, so what's going on? I have two cases. That wasn't the luckiest thing. I have one case where mu1 will be 0. And I will have one case where mu1 will be 1. When mu1 will be 1, I will have g1 squared minus p1 g1. And when g1 will be 0, then I will have g1 minus p1. And then I have to integrate both cases. The point is that here I'm missing the Grassmann number, so integrating this against g1 will give me 0, and this will give me 1. So let's say I'm integrating here g1. So in this case, I will get 1. And is that correct? I think that should be correct. And in the other case, I will get minus p1, but I need to exchange those two. So I will get a plus p1. And basically the idea is that this is behaving like a Kronecker delta. If this is not behaving like a Kronecker delta, then you would need to change it a little bit, but that's just to give one idea that we can take something that depends on G and P and then take functions of Grassmann numbers and get a new expression in P. So this is a mapping from the G subalgebra to the P subalgebra. So it's a little bit like mapping Z prime to Z in that case. And we did it with an integral. All right. So that was basically a small idea how to do those computations. And today what we will be discussing is a more general choice where we will choose k of p and g to be the exponential ptg. And what this means is that I'm taking the x of p1 g1 plus dot 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 p2l g2l. And the idea will be that this will implement for us the trace of the operators. So what we were discussing was the Bravyi dictionary, which basically was a mapping between Majorana words to Grassmann words. And then we make it linear, which means that we can express any linear operator. So if I have an operator x, a linear, which is some linear operator on space 2 to the power L, then we were discussing last time that we can express this as a summation of x mu, which are just numbers, and then m of mu. And m was basically the operator basis in Hilbert-Schmidt, in the Hilbert-Schmidt scalar product, which means that we can associate to any operator. We can associate a Grassmann varied symbol. And now what we want to show today is that if I'm multiplying two operators together, then I need to integrate against P and I need to integrate against G. I need to take the symbols of both. So each one goes to a separate symbol. And then I need to use this Bravyi kernel. Bravyi or Berezin, either way, it's a B. And that's the idea that we get this formula, which is useful because it allows us to compute many observables. So for example, we were discussing this in the session afterwards, I think, not in the recorded part. But for example, X could be just some state of psi. And if Y would be a state if Y would be a state phi, then this would give us a way of computing the fidelity between psi and phi as a Grassmann integral. That's one example. You can also compute observables that way, and so on and so on. So this is useful in many ways. And I was actually checking the paper where Bravyi wrote down this formula. I will put it in the description or in the email of the recording. It's called Lagrangian representation of fermionic linear optics, and he actually doesn't give much of a proof. He just states the correct formula. So today I will try to explain why the formula works. Okay, so we are almost in the formulation. So the point is that I don't need to care about what this is, and I don't need to care about what that is, because I can use this linearity property here and do it term by term. Okay. And the first thing is to prove the formula. Sorry, the pen is broken. But to prove the formula, we have to understand what is the correct trace. So let's say I have X okay, I need to play with the finger. I have one on the desk, like on my desk there. But I don't know if this is the batteries. I think there's something else. But anyway, we have X, which is summation over mu, X mu M mu, and we will do the same thing for Y, which is the summation nu Y nu M of nu. And when we multiply them, what we need to compute is when is a product on topic. Yeah. When is a product of two Majorana operators proportional to, oh, thank you. Okay, thanks. I think it's discharging the batteries very fast. Okay, so the question is, when is this identity? Because what we understood last time is that trace of M of nu, no, this is mu. This is delta mu 0. So basically the entire index would have to be 0 because Majorana operators are traceless. So we were proving this last week. And now we need to multiply those two things. So we can multiply them together, m1 to power mu1 dot 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 m2l mu2l, and then I have times m1 mu1 dot 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 m2l mu2l. This is f2. Okay, this is just writing out the definition of the Majorana words. basically the indices tell us whether we are placing there a variable or not. Yeah, maybe the paint would be better. If I'm writing too small, it doesn't touch it, but it's until 2L. And what we need to do is we need to reshuffle it. And that's where it will start getting more interesting. So, okay, now I need to understand this, I need to move this one here. So to move this one here, when I do that, I will have m1 to power mu1 plus nu1. And then I will have m2 to power mu2 m2l to mu2l, and then I will have m2 and the new part of this. This is a 2 ... m2l mu2l. But when I'm moving this forwards, each time I'm encountering a Majorana operator where they anti-commute, and we know they are different from each other, so they anti-commute like Grassmann numbers. So I additionally get a plus minus sign, which is basically asking about the summation k from 2 until 2l, and here I will have mu k, all the Majoranas before mu1, and times mu, which one I'm moving? The first one, mu1. Okay, so I can continue doing this, and at some point I will get m1 to power mu1 plus nu1. Then I will, the second way I'm doing this, I will have mu2 plus nu2 from the second round. And then from the last round of moving them, I will get mu2l plus nu2l. But I will have a big phase factor, -1. And here I will have a summation of k larger than k prime. Here I was doing the summation over k, so until 2l. And then we have mu k times nu k prime. That's what I'm getting. So if I rewrite this, -1 k prime from 1 until 2l, but k is strictly smaller than k prime. That's an important condition. And this condition tells you that it's kind of counting in which position we were. And then mu k, nu k prime. And what I get here is the Majorana word of mu, and then XOR nu. So the binary summation here of mu nu means that we have again 0, 1 entries, and basically we are doing a binary addition of mu1, so addition modulo 2, mu1 until mu2l binary summation with 2l. And this is because if I have different cases here, basically this binary addition works. So I could have mu1, mu2, and then no. Okay. I will just show the table how it works. And then m to power mu1 plus nu1, I can have 0, 0. Then I will have 1. I can have 0, 1. I can have 1, 1, and then the swap that I'm not showing. So here I will have m Here I will have m. No. So if I make this one into a 0, but I don't have space, so I will keep it to be 1. One, 1. And here I need to have m squared, which is the identity. And the same thing I can get from mu1 binary summation. Okay. Binary summation mu1 with mu1. So the binary summation here will give me 0, here it will give me 1, here it will give me 0, and in the 1, 0 case, I will get m, and I will also get 1. Okay, so we can also write this as m to mu1 mu1 binary summation 2 mu1 because it will exactly do the same thing, 1m 1m. Okay, and that's what what this expression here means, that we do it for every entry, and basically we wrote the definition of that one here. So I'm doing it extra carefully because this is important for us to know what the trace is. Whoops, whiteboard. Crashed now or what? Okay. Maybe next time paint.